Greetings, my name's Adrian Wells. My intention is to give you an idea about applied mathematics and perhaps point out some of the differences with pure mathematics. What you've done in the past at GCSE level to a large extent has been pure mathematics, but not exclusively. And in truth, to a pure mathematician, you're looking at it because it's interesting or beautiful. It captures your imagination, whereas applied mathematics is that which you can use. It's not strictly true these days in so far as a lot of the things that we think of as pure mathematics can be applied to a whole variety of situations to solve some pretty thorny problems. In the past, it was usual to do pure and either mechanics or pure and statistics. And in recent years, in fact, from 2017, every A-level student has had to do some statistics and some mechanics, which is good because it gives you a wider basis of your mathematical knowledge. But it does create problems for some people because they're not interested in one aspect. You've got to be good at all aspects to gain good grades. So, as I said, my intention is to give you an idea about what sort of things you will meet. I can't teach you in any great depth in this period of this particular recording any of the aspects, but you will meet them in the future. So we've got 2 units, and as I've outlined, there is a slight bias towards statistics in Unit 2. In Unit 4 at A level, they are equal, but the bias is only minor. And as I've said, if you're interested in good marks, you need to be moving and producing some good aspects. So what I want to do is to look at some of the areas. Now, a lot of the areas of statistics, the probability work, the diagrams that you will use in statistics, cumulative frequency diagrams, box and whisker plots, you've covered at GCSE. The A-level topic will take it, or AS level topic in this case, will take it a little bit further, insofar as you'll probably look at outliers. If you haven't had them introduced before, you'll work on those sorts of aspects. With a box and whisker plot, if anything is 1.25 of the interquartile, 1.5, of the interquartile range above the upper quartile, or below 1.5 times the interquartile range below the lower quartile, then you would consider it to be an outlier, and you have to see whether it actually belongs in that population that you're describing. A lot of the mathematics we've done at GCSE and the probability work that we do at GCSE is enhanced at A level. It isn't that radically different or that much more difficult, which is easy to say when you've been doing it for a lot of time like I have. So I'll move on to look at some particular things. Now, if you want to compare 2 distributions, you really need to look at where their centers are and how spread out they are. And so really the new bit at AS is this introduction of a better measure of spread and perhaps a more formalized notation. The notation I've used lower down the page, the X with a little bar, is simply a shorthand for the mean of a set of values. And you've got both versions there for raw data, where you've just got a simple list of probably a few pieces of data, maybe up to about 10, or you've got a grouped frequency distribution, and those are how you'd calculate those things. You did the means at GCSE, and you know your measures of center are mean, median, and mode. and you also did some spread work at GCSE. I mean, the most basic level of spread is range, but of course an extreme value will affect your range. You refined it with box and whisker plots and cumulative frequency diagrams to interquartile range. That's where you knocked off the top 25%, the bottom 25%, so you're only looking at the spread of the middle 25%. And what we're introducing now is something called a standard deviation, and you will hear the words variance and standard deviation, and you will see there is a notational issue here, because some people would say that this little sigma, which that is a lowercase sigma, this symbol here, and my pen seems to have stopped writing, so this is a lowercase sigma, but some people would say that should be an S if it's a standard deviation, and that the sigma should be used for the unbiased estimator, and that's where it's divided by n-1, but that is really going into other things. Variance is simply S squared or sigma squared, and it's a measure of spread. But the smaller your standard deviation, or the smaller your variance, the more consistent the data is. So don't get hung up on notation. They're easy enough to calculate. If I do it with some simple numbers, and being a mathematician I always cheat, and if I consider the numbers, let's say 1, 3, 5, 7 and 9 just as an example, it's fairly obvious in this particular case that my median and my mean are the same thing. So I can see, because I cheated and used numbers that are equally spread, then I can actually do that. But of course my x bar is going to be 1 plus 3 plus 5 plus 7 plus 9, all divided by 5. And last time I checked, 1 plus 3 gives me 4, plus 9 gives me plus 4. Try again. 1 plus 3 plus 5 gives me 9, 18, 25. So I've got 25 over 5, which gives me 5. So as I said, my median and my mean are actually in the same place. I don't have a mode in this particular case because my data only occurs once. If I want to calculate my standard deviation, and I'm not going to quibble about, WJC quite happily use the notation sigma, so that's what I'm going to use in this particular case. As I said earlier, some people say that should be an S. Then I need, as my formula said, I need to know the sum of the x squareds divided by the number I've got minus my mean squared. Okay, so in order to do that, I've got to know what the sum of the squares is. So I need to know the sum of the x squareds, which of course is 1 squared plus 3 squared plus 5 squared plus 7 squared plus 9 squared. Squared seems to have disappeared from that, which is going to be 1 plus 9 plus 25 plus 49 plus 81, 130, 155, 164, 165. So my standard deviation would be 165 divided by 5 minus my mean squared, which in this case happened to be 5 as well. So 165 divided by 5. 5 goes into 16 3 times, 1 remaining, so it's going to be 33 minus 25, which is going to be the square root of 8. And as mathematicians, we know that we can use our calculators to find the square root of 8, but on the grounds that it is the same as the square root of 4 times 2, we'd call that 2 root 2, and that's a measure of my spread. If I increase the spread, if I had them 3 apart, I'd get a bigger standard deviation. Now, there is a reasoning for that, but we won't spend too long looking at it. It's a measure of how spread out things are from the center. And if I look at those sorts of aspects, you can see that 1 is 4 below the 5, 3 is 2 below, 7 is 2 above, and 9 is 4 above. And the sum of that would give me nothing, because the sum of my spreads from the mean, which if you think about it as x minus x bar, which is going to be minus 4, minus 2, 0, 2, and 4, sum of that and this big capital letter sigma is clearly sum of, is 0. So what we do is we square things to make them work better. Okay, and so we can do it that way as well. And so it's getting a little bit disjointed here, but never mind. So if I do my x minus x bar all squared and I sum that thing, I'm going to get 40, because I've got 16 plus 4 plus 0 plus 4 plus 16. Nice symmetric distribution, but that's because of the numbers I chose. And my standard deviation, sigma squared, which is my variance, is going to be the sum of the distributions from the mean squared divided on average by the 5 that I've got. So I've got 40 over 5, which gives me 8, and therefore I'm back to this again. I need to square root the 8, and I've got my 2 root 2 again. So that's what we're actually calculating there, and that's more or less what you're doing. Now, clearly I haven't in this particular case gone into it for frequency distributions, but most of us use tabular forms, and your calculator is very, very good at doing this. Venn diagrams are a newbie. I have included at the bottom of this a link to a GeoGebra app, which this is what comes, these diagrams come from that particular GeoGebra app, and you have to actually click on sections to make it behave itself. So Venn diagrams can have 2, 3, 4 sections. They always should have a universal set, and that's typically expressed by the rectangle that you can see, and it's usually annotated with a U. And not to say that mathematicians are lacking imagination, but quite frequently the set that you're looking at are A's and B's, or letters that correspond to what those sets are. So if you're looking at people who study maths and geography, you'd use M and G. Yeah. Imagination. Mathematicians, I'm not sure those two words go in the same sentence, although they must have had a lot of imagination to have worked out some of these things that go around with us. So this diagram here, and there are some new notations to learn. This diagram here is the union of A and B. That's everything that's in A joined with everything that's in B. But it doesn't include the things that are outside A and B. Another one that frequently occurs is an intersection, A intersection B, Some people call that A cap B, A intersection B, and that's only those things that are in both A and B. This little beauty uses the dash notation. So the dash notation A dashed, for example, is that which is not in A. So this little beast here, I'm going to write it above it because I haven't got sufficient space, is B intersection A dashed, all dashed. So you think about it, the only bit that would be unshaded in that bit, because B intersection A dashed is the crossover of everything that is not in A and B, which just gives me that crescent shape. In B should be green, but then because it's a dash of that, I want everything that's not there. So what I've got is this, and it can be annotated a slightly different way, so you can actually look at it in a different way. Now, it's this sort, the three sorts, that is the most common questions that you're going to meet in AS mathematics. And obviously what I've got here, you can see the little shaded bit is the intersection between the three regions. So it's A intersection B intersection C. There is a question for you to consider where you want to put those brackets, because is A intersection B intersected with C the same as A intersecting with B intersecting C? Need to think about that one. It's not unusual with questions like this to actually have numbers in some sections and not in others, and have to work out related probabilities. So, okay, you'd need to know how many people were in the universal set and how many people would be in. So if I put in numbers here, let's say there's 3 there, 1 there, 1 here, and 2 there. It's not drawn to scale, and my universal set has got, say, let's 40 in it. Then the probability of A is going to be everything that's in A, which last time I checked, 3 plus 2 gives me 5. It's 7 over 40. Okay, so you can use it for probability type questions. Then we get on to some discrete distributions. Now, you may or may not know this word, discrete. It simply means that they can only take particular values. So for example, if you roll a fair die or dice, whichever you prefer to call it, then you can't get a 3.5, but you can get a 3 or a 4. So the distribution for a die is discrete, whereas your height is continuous, because although we round it to perhaps the nearest centimetre, it could be measured much more accurately than that. So we're considering in this particular case at AS level discrete distributions, which are relatively simple, and there are 3 distributions that you will meet. The first one is the binomial distribution, and a binomial distribution, you need to know the number of events and the probability of an event occurring. So notation we'd use for this is that x is binomial, and we've got a number of events, n, and the probability of an event occurring is p. And the probability that something in particular occurs is given by NCR, and there is a different notation for that, but I'm not using it today. P to the R, Q to the N minus R. Now, P plus Q has got to be equal to 1. You know the probability scale is a total probability of 1. So in that particular case, it's the number of different arrangements we can get, that something has happened a number of times, and that it hasn't happened the rest of the time. So it's actually relatively easy to deal with. If you want a probability that x is less than or equal to a number, you need to have all the probabilities up to the probability that x equals r, and you need to add them together. Now, that's a tedious operation, and the idea of mathematics is to make life easy for ourselves. So we either use tables, and you would be provided with a set of tables, or when you come onto things like this, there's a nice little white Casio calculator which you might like to consider, because it will do a lot of this work for you. And it's the Casio 991EX. They are about £25, and it can do all of the distribution work that you would need for AS and A-level mathematics. It'll do it for you, but you have got two things. If you want this, you'd need a binomial PD, which is a probability distribution. If you want this, you need a binomial CD, which is a cumulative distribution. And you need to think about which bit it is you want. Not particularly difficult things to do, not particularly problematic. Always look for the two pieces of data, though. You need to know N and P. If you don't know a number of events and the probability of an event coming on, then it probably isn't binomial. A Poisson distribution, and we know that the French word for fish is poisson. It's actually after somebody's name. Very clever mathematician. This just has one parameter. Now, Poisson distributions, they're easily defined because they have one parameter. My binomial had two parameters. And you're looking for things that occur at a constant rate. So you're looking for constant rates, that they occur independently and randomly. And really the important thing is that if one thing occurs, it doesn't cause another one to occur. But you've got to be looking for that constant rate aspect. So with the Poisson distribution, the only thing we need to know is the parameter. But the probability that a Poisson distribution takes some particular value is e to the minus lambda, where e is Euler's constant 2.718 squiggly bits. Lambda to the r over r factorial. That really isn't particularly well written there, because I've written my factorial bit in there. R factorial, of course, is r times r minus 1 times all the way down to 1. So this bit here, which I've run out of space, is r factorial. Okay, and again, we'd use tables or calculators if we want probabilities. And one important thing to remember in these particular cases is if the probability, we want the probability that x is greater than an r, we're into a cumulative distribution again, but it's always 1 minus the probability that x is less than or equal to r, because total probability has got to be equal to 1. Otherwise our number system doesn't work the way we want it to. Uniform distributions, well, they're nice and easy. You're used to uniform distributions. The probability when you're rolling a die is uniform, because if it's a fair dice or die, then the probability of each of the numbers coming up should be equal as 1/6. So a uniform distribution, the numbers you can get are 1, 2, 3, 4, 5, or 6, and the probability that each of them comes up is 1/6. And they're typically drawn as stick graphs or bar line graphs, and the probability that x is less than or equal to 3 is only that section there. So it's this probability. So I could do it as the probability of 1 plus 2 plus 3, or I can actually do it as quite simply 3 times 1/6, which is clearly going to be equal to half. So uniform distributions are really quite simple. You won't spend a great deal of time dealing with them, but they do give rise to some interesting things. This is where it becomes interesting. This is where statistics really comes into play. This is where you use a statistical measure to see whether something is relevant or important. And so if I said, right, I've got a fair coin and I'm going to spin it 10 times. If it's a fair coin, then, and I spin it 10 times, the probability should be equal to a half. And what we do is we set up what we call a null hypothesis, that the probability is a half. And we set up an alternate hypothesis that the probability is not a half, or it's greater than a half, or less than a half, depending on what I've got. So if I got 7 heads in 10 spins, is it biased or not? Well, from my calculator, the probability that x is less than or equal to 7 is 0.945325. So the probability of getting 7 or more the probability of getting more than 7, I apologize, is going to be 1 minus that, which is a nice little number, 0.54 squiggly bits. All right, and that would probably lead me to suggest that my coin is not biased, because it could happen more reasonably. So if this is about bigger than about 5%, we tend to stick with H0. So we imply that there is insufficient evidence to reject H0. We have to accept that it probably is a fair coin. If, however, we'd gone to 8 heads, there is then sufficient evidence to reject H0. But this is where statistics comes into a useful point of play. Vectors are easy. A vector, you will see them written in all sorts of forms. You'll see them with either bars or bolds. Obviously I can't draw bold, so I'm going to put a bar across it. And you'll see them in different notations, so 3i plus 4j. Now I personally, because my writing is as poor as it is, don't like writing i's and j's, so therefore I write my vectors as 3, 4. And that simply means that I go 3 across and 4 up, and here's my vector 3, 4, and it represents a movement. You notice I did actually put an arrow in there. If I could draw a straight line, the arrow would be on the straight line, but I can't. And we always use convention. First number, the I notation, is in the positive x-axis, and the J notation is in the positive y direction. Clearly, if I want to go the other way, so if I was looking at this particular vector, then the one that goes that way would be going the other way. Minus 3, 4. So it's minus v. So really quite simple. The other things we can do with vectors is we can find the length of the vector. Again, you'll notice as soon as you saw me write the 3, 4, you'll realize that the length of that vector, and we use modulus notation for this, is simply going to be given by Pythagoras. So it's going to be the square root of 3 squared plus 4 squared. Of course, the square root of 3 squared plus 4 squared is 5. So that's the magnitude of the vector, or the length of the vector, or the modulus of the vector, and it will give me an angle, and that angle, it doesn't matter what symbol I use. The angle of action, if you like, is quite simple, that alpha will be the angle whose tangent is 4/3 arctan, and being an old school sumsist, I know that's about 53.1 degrees to 1 decimal place. It's not exact, but it'll do. So vectors are relatively simple. Now we can use vectors in all sorts of forms, but they're not difficult things. You didn't do many of them as at GCSE. The only time you met them at GCSE were in translations, i.e. moving a point, but they're not difficult pieces of mathematics. You can get them to work. If you want to add two vectors together, then it's not a problem. 1, 2 plus 3 minus 5, and it doesn't take a raving genius to work out. I don't know why I put a minus when I said 3 and then wrote minus 3. Muppet. 1 plus 3, last time I checked, gave me 4, and 2 minus 5 gives me minus 3. And so I can actually apply those sorts of things. So I can have a force that is working there. No real problem, and I'll talk about forces again in a second. Kinematics, then this is your constant acceleration system. Your subatic systems, you probably have met them as XU-VATs in physics. As I've said in another thing that I've done recently, mathematicians tend to use S because S is the Latin for distance, spatium. Physicists use X, but a mathematician would say, well, that only means you can only go in the X direction if you're using XU-VAT, and of course we get things that go up vertically up. We get things that go in all sorts of different angles, as you will meet later on in projectile work. So we don't tend to use that, but they're constant acceleration questions, very, very similar to physics. You know, the idea is that you've got v equals u plus at. S equals ut plus a half at squared. V squared equals u squared plus 2as, s equals u, yeah, you name it, you've got them. They're relatively easy to deal with. They actually do come from the idea of gradient, but you work into rates of change. So you've got things like velocity is the rate of change of distance with respect to time, and that requires calculus. Acceleration is the rate of change of velocity with respect to time, but it's also the second differential of distance. So you've got second differential, so you bring in a lot of calculus, whether it's Newtonian, whether you describe it as Newtonian calculus. Most of us use Wallace's rule to to use differentiation, integration, area underneath curves. So if we've got a velocity time graph, and we're dealing with constant acceleration systems, then the area underneath that is the distance travelled. So that's more or less what we're talking about. And here we get into forces and Newton's laws. And really, Newton's laws, relatively simple, straightforward. The main one that we're interested in, what most people call Newton's second law, N2L, and that is force is equal to mass times acceleration. But there are other ones that are theoretical laws, that a body will remain at rest unless a force is acting upon it. You know, if you've got something sitting on the desk, it doesn't do anything until you do something to it. It's by and large incapable of moving on its own. So, but the main one we're interested in is something like a force equals mass times acceleration. Let's say I've got something like a mass of 10 kilos, 10 kilograms, and I've got a couple of forces acting upon it. Little point here to a mathematician, G is always used as 9.8 newtons. Okay, and we use 9.8 because it actually cancels nicely with lots of other things, but mathematicians use G as 9.8, and if we've got some forces acting on it, or I've got a force acting that way, let's say I've got a force acting that way of 4 newtons, and one acting this way of 6 newtons, and a further one. Now I'm going to chuck in a vector here, and you remember I used vectors earlier. So you can see this one's acting at 45 degrees. Then my total forces acting overall are going to be 6 plus 1 in the forward direction minus 4. Because if it's got a mass of 10 kilograms, a force of 1 newton acting up isn't going to shift it much. So what I'll get is an acceleration in that direction. So I think I've got a force acting forward of 3 newtons. I've actually got a force of acting up of 1 newton as well, but the acceleration will be that way. So 3 is going to be equal to 10a. So clearly a is 3/10 meters per second squared. So really simple ideas, simple diagrams. Notice I wrote 10g is because I would normally, when I get a bit better, go on to normal reactions, and those two forces, vertical ones looking up, and so I've got r plus 1 is equal to 10g because that is a force going down. So r is 10g minus 1. I get friction coming in, but that's not till later on. So as I said, all I wanted to do was to give you an idea about some of the things that you're going to meet in applied mathematics. If you've got any questions, there will be clarifications further coming on. There are also going to be some linked worksheets with these. Then if you email, then we will take the time to respond to you. I wish you well in your studies. These are opportunities for you to develop your mathematical thinking, develop your reasoning, your logic, and remember that mathematics, I will hold my hand up here to being completely biased. Mathematics is the queen of sciences. Without mathematics, science wouldn't exist.